Today we are going to derive a version of substitution for double integrals. Recall that for a Calc 1 integral, so if we have something like the integral from a to b of some function f of x dx, and we want to replace the variable x with another variable u, what we can do is we can write x as a function of u. And so we don't have to actually keep introducing more letters for functions. I'm going to just write it as x of u. What we then do is we differentiate this thing. So this is a function of u. We can differentiate with respect to u, and we get the derivative dx du. Of course, we normally would write this as dx equals that derivative times du. And then we would replace the x that's in here with x of u, and we replace the dx with the derivative times du. So we have f of x of u. So this is now a composition that is of u overall. We have the derivative du, and then we'd have some limits here, c and d, where we find those limits by just saying that a equals x of c and b equals x of d, and we have to solve for c and d. Now this is not normally how we actually approach substitution normally. Normally we start with something where we try to recognize it as something of this form, recognize that a derivative that's inside the integral, and try to get rid of that derivative by making some sort of substitution, and end up with something over here. That helps not only with the limits, but it normally will actually make something a little bit simpler over here that doesn't have this extra factor in it. But this is also the process that we use for stuff like trig substitution, where we start with some function over here, we introduce a trig function, we essentially will replace our variable with some trig function of usually t or theta, and we introduce the derivative as extra trig functions that hopefully will be able to simplify the actual integrand. It's also the process that's going to be much easier to generalize to double integrals. So this is the version of substitution that we want to really focus on for this section. Normally when it comes to doing stuff with double and triple integrals, we don't really call this just substitution. Normally we will refer to this as change of variables. The idea here is that we have some set of we have our normal set of variables x and y. We're focusing on 2 dimensions right now. We'll talk a little bit about 3 dimensions later. We have some variables x and y, and we want to somehow change those to some new variables u and v. U and v are generally the standard ones the standard letters to use for this. But let's look at a particular example that we already know how to deal with. Polar coordinates. Of course, there instead of u and v, we use r and theta. So we want to change from xy to r theta. And we use the formulas x equals r cosine theta and y equals r sine theta. So just like what we had back here with our function of one variable, we have our old variable in terms of the new variable. Here we have our old variables of x and y in terms of the new variables r and theta. And that's generally what we'll actually be seeing. And sometimes when we actually have it the other way around, we'll end up having to solve to get formulas like this. So maybe in some situations you might have r and theta in terms of x and y, or the equivalent with u and v in terms of x and y, and you have to put it the other way in order to use some of our formulas here. And so for our general change of variables, we'd have, so in general, we would have x is some function of u and v, and y is some function in terms of u and v. Now, one thing that we do actually do is consolidate this a lot of times into one function of two variables that has two variables as its output. So this is actually a function from R2, so it's taking in two variables to R2. It's giving out two variables. Generally the way we want to think about this is that we have a plane, a UV plane. So points here are points UV. We have another plane over here. This is the regular XY plane that we usually think about. So we have points over here that have coordinates of XY. And the idea is that the function t takes a point over here to a point over here. So it maps this point over to this point where this is t of uv. But normally what we can do here is say that x is a function of that u and v, that this function gives us the first coordinate, this x here, and then this function gives the y coordinate, this y here. We generally will not write this in terms of, in this way, we'd write down formulas like we did for polar coordinates. So while this notation is going to be useful for actually doing some of the theory behind this, in practice we generally write down just a formula for x and a formula for y. We are going to replace a few restrictions on what t's we can use. And by the way, first of all, I guess we should note here that we call t a transformation. But our restrictions here, first of all, we want it to be a C1 transformation. And in fact, everything here is going to be assumed to be this restricted type of transformation, even though I'm just going to use the term transformation. What C1 transformation means is that all the functions that we're dealing with, the x and the y, in terms of u and v, have derivatives. Or I should write these as partial derivatives, sorry. So partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. These are all continuous functions. Not only do the derivatives exist, but they are continuous. That's what C1 means. It's actually a broader term in mathematics, referring to continuous first derivatives. C2 would be continuous second derivatives, and so on and so forth. But here, just be aware that we can differentiate these functions. The continuity part we generally will gloss over. It's technically there, but we generally don't have to draw too much attention to it. The main thing is that if we don't have derivatives, none of these formulas are going to work. So because the formulas are going to involve derivatives. Just like how when we worked with substitution back here on the first page, we definitely need to be able to differentiate x with respect to u, or else none of this makes any sense. The other condition here that is also going to be a little bit lax, we're not going to be super concerned about it, but we'll kind of assume here that things are going to be one-to-one. That means a point over here, a point xy, for a general function t that does something like this, maybe there could be some uv that maps to it, but also say, I don't know, let's do u1, actually let's do, I don't know, let's just use different letters. Let's say rs. If there's another point rs over here where this is also t of rs, a completely brand new point, two different points mapping to the same point through this function, it would not be one-to-one. Being one-to-one says that this cannot happen. And a part of the reason why we like to do that is that we can actually find an inverse transformation. Some t inverse that takes the point xy that we have over here and gives back the point UV that we have over here. So if we have two different points that go to this point, then where would it map back to? If there's only one point that maps over here, then we can say unambiguously that that point would map back to its original point. Now, the reason why I'm saying this will be a little bit lax in overall is because we have things like polar coordinates. If we plug in, say, 0 and 2 pi, we're going to get the same points for x and y. If we have the same r, but then our theta is 0 or 2 pi, then we're essentially putting in two different sets of numbers and getting the same result for x and y. And yet we still want to call this a transformation. Mostly what that will mean for us is that we are not going to worry about it when it comes to the boundary of our regions that we'll be integrating over, and generally that will be enough to get past that problem. In fact, it'll be mentioned in the theorem that we get to eventually that we assume that it's 1-to-1 except maybe on the boundary. But there will be a few situations, a few examples where we'll actually we'll be either given the inverse transformation somehow, or that's the thing that will be easiest to come up with, and then we turn that around to find the original transformation. So I definitely want to be aware of what the inverse transformation is. It's just going the opposite way from what this t is. So taking points in the xy plane, giving points back in the uv plane. Now the main idea here is, let's say we want to take an integral, a double integral, of course. We have some region in the xy plane. We'll call it R. In fact, we'll stick with R for regions in the xy plane for most of what we're doing here. So we're trying to take the integral over R of some function of x and y. Well, over here in the uv plane, where we know there's a transformation from uv to xy, we want to say that there's some other region here. Actually, let's maybe make this a little nicer looking. Maybe it's some rectangle, though it doesn't have to be. We'll call the region over here S. We essentially want to say, is there some way we can convert this integral here into an integral over here? So an integral over S instead of some function of u and v. Can we find some function that we can replace f with in terms of u and v, and some way to relate s and r in order to make these two integrals give us the same result? Where maybe this one's a lot easier because we made it a rectangle instead of some more blobby shape. Now, the first thing that we're going to tackle here is what is s with regards to r? Because there's going to have to be some relationship between s and r via this t. Finding out what the actual function changes to is going to actually depend on us being able to do that. Well, the main idea that we want is that points in S, so say some point here, needs to end up in R somewhere. Every point in S needs to map into R. And we don't want any extra points in R that didn't come from points in S. If that's true, we say R is the image of S. So let's first actually look at an example in polar coordinates. So here I'm going to have two different graphs. This first graph is going to be the r theta plane. And note that we're not thinking of r and theta here as the distance from the origin and the angle around the origin. We're thinking of points in this plane as literally just being, so a point here, let me even just plop a point in there. The r theta values for this point are just going to be the distance along this first axis. The GeoGebra was calling it the x-axis, but we're going to think of it as the r-axis. Then along this axis, this will be our theta axis. So I plop that point there. It's saying x is 3.2 and y is 3.78. Really, we'd be saying that's the point where r equals 3.2 and theta equals 3.78. Then our transformation is going to take, say, this point here and plot it over here into the xy plane. So if we put a point over here, so I want to take the point where r is equal to 3.2 times the cosine of 3.78, and then y is 3.2 times the sine of 3.78. We get this point here. That transformation, our formulas for polar coordinates are taking this point in the r theta plane and plotting this point over here using that polar coordinates. So this is a distance of 3.2 from the origin, and the angle, in radians at least, is 3.78. Now the idea here is that we want to take a particular region in the r theta plane. I'm going to actually go ahead and let's get rid of these, and I'm going to plot some points. By the way, I picked the particular plane that I'm putting the points into by first clicking on that plane. So I click over here, and then I type in a point, and it will plot that point in this one and not that one. So first I'm going to go ahead and I'm going to look at a rectangle in the r theta plane. This is going to be the rectangle where r is going to go from 1 to 2, and theta is going to go from 0 to pi over 2. So I'm going to plot the point 1, 0, 1 pi over 2, 2, 0, and 2 pi over 2. This is a rectangle. And go ahead and even connect those. And let's not display all those names. Okay, we have a rectangle over here. Now, when we're actually plotting things over here, if r is going from 1 to 2, we're really looking at circles around the origin of radius 1 and 2. So we have two circles there. And saying that theta goes from 0 to 2 pi, 0 to pi over 2, really just means that we're looking at angles between an angle of 0 and an angle of pi over 2. We're looking at this region here in the first quadrant that's between the two circles. So in fact, this region here is the image of this rectangle. This is the base rectangle that's mapped over here to this quarter of an annulus. Remember, something like this we were calling a polar rectangle. And it's because under these transformations, it really did come from a rectangle in the r theta plane. Basically, when we wrote it down, it would actually give us the same format for a rectangle. If we wrote it down, we'd have something like, we're calling it S. This is the set of all points r theta, where r is between 1 and 2, and theta is between 0 and 2 pi. Sorry, not pi. I keep wanting to say 2 pi. It's pi over 2. This format that we wrote down is exactly the way we wrote down rectangles in rectangular coordinates. And the fact that we could write it down this way is why we liked it so much when we worked with polar coordinates. Even though the actual regions that we looked at were not really rectangles. They were definitely not rectangles. It's because if we're thinking of this in terms of transformations, we really are working with rectangles back in the original r theta plane. Let's try this with some transformations that we're a little bit less familiar with. So here we have a particular transformation. So we have variables x and y in terms of variables u and v. We have a region. They're telling us it's a triangular region in the, well, they kind of expect us to realize that when we're talking about S, so they're using the letters R and S for the region in the XY plane and the region in the YV plane. They're using S for the YV plane. So these are coordinates in the YV plane. Normally we'd want to be a little bit more specific to make sure that we know what we're talking about. They're kind of relying on us remembering what letters they're using for which one. So kind of a little annoyed by that, but we can make do. But the point here is we're going to go ahead and graph this. So again, we have our YV plane and our XY plane. We're going to plot the triangle that we're working with in the UV plane. So that has points 0, 0, 1, 1, and 0, 1. And of course they told us it's actually a triangle. Those are, yeah, there we go. Let's zoom in on that a little bit. And I want to keep this text on the frame. Okay. And I'm going to go ahead and remove the labels of those. There we go. I'll keep the labels for A, B, and C. That way I can actually show where those points go to over here. So we want to see what happens to this region, this triangular region, which we can even go ahead and label. This was S. So we have region S. Let's make that a little bit bigger so we can see it a little bit better. Let's make it large. In fact, I want to make these labels large as well, so they stand out better. There we go. We're going to take the points in this triangle and plot them over here and see what we really get. Now, let's actually just go ahead and maybe try some points. So let's see what happens to some various points. So if we have a point, so let's just go ahead and put it here. If we have a point UV, where does it end up when we put it into X and Y? Basically, what happens to it when we go through these formulas? Let's start with the vertices. We have 0, 0, we have 1, 1, we have 0, 1. What happens to those when we plug them into this formula? Well, y equals v, so actually the third coordinate here doesn't actually change. Those are all just 0, 1, 1. The x coordinate is just u squared, so we get to square these. 0 squared is 0, 1 squared is 1, 0 squared is 0. So actually these points didn't change. Let's go ahead and plot those points over here. Now I'm going to label them similar to what we have over here. So point A was 0, 0. I'm going to say that the point A2 is going to be its image of 0, 0. So it's going from this point over to this point. Point B was 1, 1. So B2 is going to be 1, 1 because that's the image of 1, 1. And then C being 0, 1, the image of that point, C2 was also 0, 1. So we need to actually zoom in onto this one. There we go. Well, if we got the same vertice points, do we still get the same triangle? Does that mean our image is the same triangle? Well, not really. If we take some points on the boundary, we might see what happens to those. So let's take some points. Let's take the midpoints of the boundary of the triangle. So on On the y-axis here, we could take the point 0, 1/2. Or on this boundary here, we could take the point 1/2, 1. And on this line here, we could take the point 1/2, 1/2. In fact, let's even go ahead and plot those points. So we'll say D is going to be 0, 1/2. Oh, I'm in the wrong plane, sorry. I want to put it over here. D is going to be 0, 1/2. E is going to be 1/2, 1. And F is going to be 1/2, 1/2. Those are all points on the boundary. What happens to those points when we put them through these formulas? So 0, 1/2, our first coordinate is going to be the first coordinate of this one squared, so 0 squared is 0. But our second coordinate is just going to be the second coordinate that we have there. So that just stays as 1/2. So that point doesn't change. 1/2, 1 is going to be a little bit different though. When we plug in 1/2 into u squared, we get 1/4. And then the 1 just stays as 1. If we look at 1/2, 1/2, this time this 1/2 becomes a 1/4, and that 1/2 stays the same. So we get 3 different points, which we can go ahead and plot. Make sure we put them over here. So I'm going to continue with the idea that I'm just going to attach 2 to the names of these points. So D2 is going to be 0, 1/2. E2 is going to be 1/4, 1. So it is still on that same line up there, but it's now at a different place. And then our F2, this is going to be 1/4, 1/2. It is now no longer on the line between A2 and B2. Now it's kind of moved over. And we want to figure out exactly how does that fit in. Now we could keep plotting points here, and we could keep going through all that stuff, but that's can be a little bit tedious. If there's vertices like these first 3, generally we'll go ahead and just do that. Or at least in general, we might think about doing that. Normally with the boundary, we instead look at how the formula for the boundary curve changes. So we know what the actual curves are for the boundary of S. They're lines. We know what those lines are. So we have the line from, say, 0, 0 to 0, 1. That's going to be the line x equals 0, at least between y being 0 and 1. How does this change in terms of u and v? Well, if x equals 0, these points are in terms of u and v. There should be u equals 0. It's actually the v-axis, so u equals 0. How can we change this into something involving x and y? Sometimes we have to be a little bit clever about that. In this particular case, what I might do is I might square the u. So u squared equals 0. So I'm just squaring this formula. But u squared is x. So the line u equals 0 actually changed into the line x equals 0. Which actually kind of makes sense. So the points along this line here were not changing at all. Even the midpoint that we took there was still that line. So that's still the y-axis here between those 2 points is still one of our boundary curves. The line from, say, 0, 1 to 1, 1, so that's our top line here, that's the line where u equals 1. Or, sorry, v equals 1. So, yeah, v is this axis here. The v coordinate of all these is equal to 1. Well, v is u. Or, sorry, v is y. So v equals 1 is the same thing as y equals 1. So the fact that E2 did end up on the line from B2 to C2 was not a coincidence. it does end up on that line. It doesn't mean we map to the same point, but this line here, this entire line, does map to that line as well. Every point on here maps to that line, and every point on this line, and on this line segment, came from somewhere on this line segment. Let me get those labels out of there. Now, of course, this third line segment is going to be the more interesting one. Remember there, that is the line u equals v. We're going from 0, 0 to 1, 1. Obviously, those are points in the line u equals v. This time we're going to have to figure out exactly how do we convert that to x's and y's. Well, we'll make the same kind of trick that we did for this first one. We're going to square everything first. So u squared equals v squared. Well, u squared is x. V squared is not y, but v is y, so v squared is y squared. So the line u equals v corresponds to the curve x equals y squared. So if we go ahead and plot that, oops, I did not want that. If I plot x equals y squared, it goes ahead and puts in this parabola. It is a parabola. It's a sideways facing parabola. And the part of the parabola between A2 and B2 is, in fact, the image of this line segment. If we actually continue that line off in both directions, we get this entire parabola. We're really just concerned with the part that's between A2 and B2, but it does pass through F2, which it makes sense that the point F on our line segment here needs to end up on this curve. So this region S, in fact, corresponds to this region over here, R. I don't know why it won't let me change the size unless I'm going to the properties. I can't do that from the original menu. But basically, this triangle S turns into this not quite triangle R. It has a curved side on it. So once we actually develop our formula, we'd be able to use the ideas that we have from this transformation to integrate something over this region R by instead integrating over this triangle S, which may be easier, depending on the situation. Most of the time, we'll actually look at regions R where it's actually a really annoying one to integrate over. This one wouldn't be too bad. I mean, this is actually both a type 1 and type 2, and so it wouldn't be too bad to just do the integral directly. But in general, we can actually tackle things that would be really painful to do by type 1 or type 2 methods. More commonly in problems, we'll have the image, the R, instead of the S that we started with. Normally, we'll be trying to figure out, can we find an S that maps to the R that we're given? So here, we have the region R in the xy plane. It's a parallelogram with given vertices. And we want to find some rectangle that maps to R, because rectangles are going to be a little easier to work with. Let's go ahead and plot this parallelogram, and I'll discuss it a little bit more when we've done that. So we want to graph our points, our vertices of our parallelogram. So those are the points 0, 0, 4, 3, 2, 4, and negative 2, 1. We have these 3 points, or 3. We have these 3, 4. We have these 4 points. I don't know why that was so hard to say. We'll go ahead and connect them to actually make the parallelogram. So this is going to be our region R. And before we actually get started on finding out what S is going to be, let's just note here that if we wanted to integrate a function over R, a function in 2 variables over R, this would actually be kind of a pain. This is not a type 1 or a type 2 region. If we wanted to think of it as a type 1, we'd have to think about what would be our top function, what would be our bottom function. Between negative 2 and 0, we have this line as our bottom function and this line as our top function. But once we pass 0, as we go from 0 to 2, now this line is our bottom function, and while this line stays our top function. And then after 2, now this line is our top function, and this line is our bottom function. We'd actually have to divide this parallelogram up into, say, 3 different pieces. This triangle over here, this parallelogram in the middle, and then this triangle over here. We'd have 3 different pieces. We have to do 3 different integrals if we're going to do that. If we do that instead as a type 2, we'd do kind of the same thing, where we'd have to kind of, from 0 to 1, we'd have to use this triangle down here. From 1 to 3, we'd use this parallelogram here, and from 3 to 4, we'd use this triangle here. Again, kind of annoying. So that's one of the reasons why a transformation would not be bad to do here. It actually might make things a lot easier. It just depends on how much setting up the actual transformation would actually save you time. Maybe it would actually be quicker to do 3 integrals than it would be to set up the transformation. But there are definitely situations where setting it up is far quicker. Now we want to turn this, we want to find some rectangle over here that turns into R. That answer will not be unique. There are definitely different answers that we could have here. Though the answer that we're going to get here is probably the nicest one that we could get. So the first thing that we want to do is worry about the lines that we have for our boundaries. What are these particular lines as formulas? In fact, we think about what is the line from 0 to 4, 3. If we look at that line, that line has a slope of 3 over 4, and it passes through 0, 0. Therefore, we have a boundary curve of y equals 3 over 4 times x. Now we can use the fact that we know this is a parallelogram to say that this line over here also has a slope of 3/4. We do need to find what is its y-intercept. It turns out that y-intercept is 5/2. You can find that by, well, there's multiple ways you could find that out. I'll leave that to you to actually verify that these are correct. The next one, well, let's work with this one over here because it does pass to 0, 0. It has a slope of, well, it's a negative slope of 1 over 2. So we have y equals negative 1/2 x. And of course, the last line is also going to have that same slope because of the parallelogram. We're going to have to identify what is the y-intercept here. Turns out it passes through 5. Again, I will leave that to you to verify that. And now we want to take these formulas for our boundary lines and move them around so that we can actually identify some things that equal constants. So what I did is I took these first 2 formulas, I moved everything with x's and y's over to one side. So we have negative 3/4 x plus y is equal to 0, and negative 3/4 x plus y is equal to 5/2. This expression here, this negative 3/4 x plus y, is a constant on both of those boundary regions. That actually might be something that we might want to call u, or maybe v. I mean, you can pick either one. But I'm essentially going to call this side over here u. Well, in order to not deal with fractions, I'm actually going to change this a little bit. I'm going to multiply both sides by 4. That's going to change this first equation to negative 3x plus 4y equals 0. And the second equation is giving me negative 3x plus 4y is equal to 10. So if I set u equal to 4y minus 3x, just putting the x at the back, then what we have here is that this variable u goes from 0 to 10 on the boundaries. You can do the same thing with these two equations here. Basically move the 1/2 x over to the other side. So 1/2 x plus y is equal to 0 is this first equation. Second equation is 1/2 x plus y is equal to 5. Again, let's just get rid of the fractions by multiplying everything by 2. We have x plus 2y is equal to 0. X plus 2y is equal to 10. So if we set v equal to x plus 2y, then that value is going from v equals 0 to v equals 10. So we could go ahead and plot that rectangle. So we have 0, 0, 0, 10, 10, 0, and 10, 10. Go ahead and connect those lines, or connect those points with the lines. Why does it keep deselecting the segment tool? I want to make 4 different segments, not one at a time. There we go. So we have this rectangle, or really it's actually a square in this case, that under the transformation that we're deriving here is going to change into this parallelogram R. So S is going to change into R. Now, what we have here is actually not the transformation. Remember, we want to express our old variables x and y in terms of the new variables u and v. What we've done here is actually the opposite. This is actually the inverse transformation. So you can say that's t inverse. If we want to find t, we need to solve for x and y. Now, you can go ahead and do that yourself. I'm going to just note here that what I did was I would take my formula for v. If you multiply v by 3, then add those together. The negative 3x here and the 3x here would cancel out. You're going to get a formula for y. So y is equal to, you actually end up with a 1/10 u plus 3v. If you instead multiply v by 2, that gives a 4y here and a 4y here. Then you could subtract them. You end up having to divide by 5 this time. But you get 1/5 of 2v minus u. And that is the transformation taking u and v to x and y. And the fact that it even has an inverse here, actually it can be helpful. Knowing both directions of this transformation can help you actually do various things with it. So if we want to integrate something over R, we could do it over S instead using u and v, or even vice versa if we really wanted to. As our last example for this video, let's work on problem 14. Here, again, this is similar to the last problem. We're given stuff about R, and we want to find a transformation that takes a rectangle to that R. Our information, though, is not giving us a boundaries with lines. It's not giving us a parallelogram of any sort. Instead, we have 2 hyperbolas and 2 lines. So 2 of them are lines. So we have y equals 1 over x. Let's go ahead and even plot those. Y equals 1 over x. We have y equals 4 over x was our other parabola, or hyperbola. So we have these 2 things here. But then we also have 2 lines. We had y equals x and y equals 4x. Though they are specifying here that we're working with the first quadrant. So while you could actually say there's two different regions here, we're only really concerned about one of them. And I don't want to lose that label. There we go. We have this region here. Now, what is this region, or how can we get this region in the UV plane? Of course, the result that we're going to get here, again, is not going to be completely unique. There are different possibilities, but we're just going to come up with one of them. And we want to find some way in order to relate this to something over here. Now, of course, you can kind of think, well, these different curves, there's 4 different curves, they probably are going to correspond to our different sides of a rectangle. And you'd be correct about that. It's just going to be a little bit more complicated to actually determine what those sides are. But again, we're going to take our curves and we're going to try to move stuff around in these formulas in order to get some equation or some expression in terms of x and y equaling a constant in 2 different ways. So we'll start with the y equals 1 over x and the y equals 4 over x. So I'm going to take these formulas, and if I multiply both these formulas by x, it turns out really nicely. So if we multiply this first one by x, we have xy equals 1, and then we have xy equals 4. We have the same expression in terms of x and y equaling 2 constant values. If we set u equal to xy, then that means that u is some value going from 1 to 4. And that's actually pretty nice for us. Then we take the other 2 lines, or the other 2 boundary curves, so y equals x and y equals 4x, which are both lines this time. We want to somehow turn these into some expression in terms of x and y equaling 2 different constants. But this time it's not quite so simple. Well, it's not too difficult, but you kind of think, well, I have lines, I want to keep things as lines, right? But it turns out the easiest way to tackle this is to divide by x. If we have y over x equals 1 and y over x equals 4, then actually it corresponds very nicely. But that's not probably what you expected us to do with them. So actually we're going to set v equal to y over x, so that v is something between 1 and 4. Now, of course, again, this is our inverse transformation. We have our new variables in terms of our old variables, and we want the other way around. So we need to actually solve this for x and y. You might have to play around with that a little bit. It's not necessarily a straightforward process since we're not dealing with linear equations right now. If you think about it, maybe you might say, well, if you multiply u and v together, the x's will cancel out nicely. So that's actually what I like to do, is multiply those together. So xy times y over x. The x's cancel out and you get a y squared. Of course, that's not actually y. You'd actually have y equals the square root of uv. To get x, you kind of want to do a similar thing, except this time you want to get rid of the y. So what you might do here is you might take u and divide it by v. So again, u is xy and v is y over x. When you divide those, these y's actually cancel out and this x ends up on the top. So you actually get x squared. So you can say here that x is the square root of u over v. This is our transformation. This is our t. And of course, our u and v are over here in our uv plane. Those are the points 1, 1, 1, 4, 4, 1, and 4, 4, because remember our u and v are going from 1 to 4. In fact, both of them are. And I'm just going to remove those labels. This is going to be our S. So this square here changes into this region over here through these equations. And maybe that's good enough to do some integration over this region. Whether or not that turns out nice might depend, but it is a way of doing that. This is a way of getting transformation from a square to this more complicated region that would be, well, this would be a real pain to do anything with in it directly anyways. I guess if you really had to integrate something over this, I guess this intersection point here connects nicely to this intersection point here. This is a vertical line, so you'd end up having to do two integrals if you want to do this as two type 1 integrals, or you could actually go the other way. The fact that these points actually line up nicely can make it kind of handy. You could actually do this as a type 1 or type 2, and both times you'd break it up into two integrals. But of course over here you have one integral where you don't even have to deal with top and bottom curves. You just have constants. You have an integral from from 1 to 4, an integral from 1 to 4 of whatever function that we get, and then du dv. Of course, we have not yet figured out how to change the function. The function is not just going to be the original function with u and v stuck into it. I mean, that wasn't even the case when we did substitution with one variable. So in our next video, we're going to figure out how our function actually does change. But I definitely want us to get familiar with how these transformations work before we actually start trying to do integration with them. So make sure you understand this stuff, and then meet me in the next video.